Okay, so given this utility function and this budget constraint, we want to find the optimal consumption, the x's and y's that maximize utility. The way we do this is to write down our Lagrangian, this weird L thing, which is just equal to what you want to maximize, so your utility function, plus a lambda times your budget constraint. So we write it this way: 100 minus x minus 2y. So that's the way you set up these things. You write down a weird L, set it equal to what you want to maximize, your utility function, plus lambda times the constraint. To find what we want, we do differentiate this with respect to x, y, and lambda. So when we're maximizing something, we set it equal to 0, so we get a half of x to the minus a half times y to the half. That doesn't matter, minus the lambda is equal to 0, which we can rewrite in terms of lambda, or with lambda on one side, as lambda is equal to a half x to the minus a half y to the half. So that's our first equation, call it 1. And the next one is to just do likewise in terms of y, so d lambda dy. Just differentiate, so we get a half x to the half y to the minus a half. That doesn't matter, that does matter, minus 2 lambda is equal to 0. So we can rewrite that as lambda is equal to a half x to the half y to the minus a half all divided by 2. That's our second equation. So what we're trying to get is 3 equations and 3 unknowns, which we're going to solve by substitution. So now we have 2. The last one then is just pretty simple. It's just differentiate the Lagrangian with respect to lambda. And that always just gives you back your budget constraint. Minus 100 minus x minus 2y equal to 0. So differentiating your Lagrangian with respect to lambda always just gives you back your budget constraint. So there we have our 3 equations. We want to find x and y. So let's take the first and the second. So we can just write down, because they're both equal to lambda, we can set them equal to each other. So half x to the minus a half y to the half is equal to number 2, a half x to the half y to the minus a half, all divided by 2. We want to find x in terms of y or y in terms of x. So let's just divide both sides by this. So that's going to give us y to the half is equal to half x to the half x to the half y to the minus a half all over 2 times a half x to the minus a half y to the half. Okay, so we just divide it across by this. That half will cancel with that, first of all. That's going to give us a half. What can we do here? Well, we've x's on both sides of this division. We can bring this one up to the top by subtracting the power from that. So minus minus half is going to give us x. And then we're going to have y to the minus just leave it as y to the half. Something's wrong here. Hang on. Oh, sorry, there shouldn't be a y there at top. Okay, so we were just dividing across by this. So we still have y to the minus a half there. Okay. Which of course is equal to y to the half. If we pull this power over to that side by dividing, we end up with y is equal to a half x. Okay? So we just divide across by this. It gives us y on that side is equal to a half x. Okay, so now we can go back to equation 3. So equation 3 tells us that 100 minus x minus twice y is equal to 0. Well, we know what y is. We know it's a half x. So it's minus twice of half x is equal to 0. So that means that 100 minus 2x is equal to 0, or x, our optimal x, is equal to 50. Okay, so now we know what our optimal level of x is to maximize utility. What about y? Well, we know that whatever our y is just equal to half of whatever our x is. So y star is equal to a half of x star, or 25. Okay, so now we know our utility maximizing x's and y's. We also want to know what level of utility we get at the utility maximizing bundle. So u of 50 and 25, well, that's pretty straightforward. You just stick in what you found to be the best x and y combination. So that's equal to 50 to the power of a half times 25 to the power of a half. So you just stick your x and y in here, which is about 35.35. Okay, so that's all we need. You could graph these things then, pretty straightforward using the stuff we learned in previous problem sets.